Welcome. This is our first lecture on basic concepts, frequency distributions, and displaying data. Before I start the lecture, I want to share a couple of little tricks that you might find helpful as you watch this lecture as well as other recorded lectures. The first is that you can watch the videos with closed captions, which can aid understanding. So in the YouTube options, make sure to select closed captions. The other tip is that you can adjust the playback speed. So if you find that I'm talking too fast, you can reduce the playback speed to 0.75. If you want me to speed up, you can increase the speed to 1.5. So those are just a couple of the settings that you can use in YouTube, which can some students find helpful. Let's start with some basic definitions. So statistics is a branch of mathematics that focuses on the organization, analysis, and interpretation of a group of numbers. Psychologists use statistical methods to help them make sense of data that they collect when conducting research. Psychologists usually use statistical software to carry out the statistical procedures like the ones we're going to learn about in this class. However, what I think, and what the authors of the textbook also think, is that the best way to develop a good understanding of statistics is to actually do the procedures by hand with the help of a handheld calculator. It's not necessarily the multiplying and the adding that you learn from, but it's going through all the steps to really understand the basics of how the statistics works. So for the most part, the examples that you're going to read in the textbook and the ones that I'll use in my lectures are going to use relatively small groups of very simple numbers, and this should allow you to focus on the underlying principles and the logic of the statistical procedures as you work with the numbers. There are two main branches of statistical methods. Descriptive statistics is the first one. So psychologists use descriptive statistics to summarize and describe a group of numbers from a research study. Inferential statistics is the other branch. So psychologists use inferential statistics to draw conclusions and to make inferences that are based on the numbers from a research study, but that go beyond the numbers from that study in order to make conclusions about a bigger population. So really the goal of inferential statistics is to allow researchers to make inferences, that is conclusions, about a large population of individuals that is based on a research study in which a much smaller sample of individuals takes part. I just used the terms population and sample, so I'll define them here. A population is all the cases, situations, or people that a statistician wants his or her inferences to apply to. Okay, we can also say that a population is a larger group to which inferences are made about by using a smaller set of people who are actually studied. A sample, then, is a relatively small selection from within the population, which is usually considered to be representative of the larger population. So a sample refers to the people or the cases or the situations that are actually studied and used to make an inference about the population. These terms are not introduced, these terms meaning population and sample, are not introduced in the textbook until chapter 3, but they're important enough that I wanted to mention them here in the first lecture. Why do we need samples? Mostly because it's impossible to study an entire population. Populations are often very large. For example, a population could be all people in the world, or all US citizens, etc. in which case it is simply impractical to study every single person in the population of interest. So many of our statistical methods that you're going to learn about in this class are tools for making generalizations about a population by using a smaller sample of people. So that's really the value of statistical methods. Statistics allow researchers to study different phenomena and to do so using a smaller group of people that is actually practical to study. Now, a very important point, which I've included down here at the bottom of this slide. That doesn't necessarily mean that all populations need to be big. Indeed, it really just depends on who or what the researcher or statistician wants to make generalizations about. It could be the case, for example, that a researcher is, or let's just say a professor, is only interested in understanding the characteristics of a particular class. There's no intention to make any inference or generalization beyond the 30 or 35 students that are currently in the class. In this case, the class of students that is only 30 students is the population because they're the entire set of things that the professor wants to make a conclusion about. Okay, so populations are often large, but they don't necessarily need to be. And in fact, some psychologists are interested in populations of people that are very unique or rare, in which case they can be very small. They're not large at all. So populations are often large, but they don't need to be. Some more basic concepts. A variable is a characteristic that can have different values or levels. Examples of variables are really anything you can think of that differentiates people. Physical characteristics like height, weight, hair color, eye color, of course things like race, gender, age, etc. There are also psychological attributes like personality, cognitive abilities, attitudes, beliefs, values. So really, any characteristics that can have different values are variables. A constant is something that could potentially vary or have different values, but only has one value. So as a specific example, if there were only women in this class, gender would not be a variable, it would be a constant. Similarly, if there were only 20-year-olds in this class, age would not be a variable, it would be a constant. Values are the possible numbers or categories that someone can have on a variable. So, for example, imagine that I ask you, on a scale from 1 to 10, how excited are you about this statistics class? The numbers, 1 through 10, are the possible values. A score is a particular person's value on a variable. So your answer to the question, how excited are you on a scale of 1 to 10, would be your score. However you answer the question, whatever number you provide is your score on the variable. Another concept worth reviewing is the idea of levels of measurement, which is simply the idea that there are different kinds of variables. The first major distinction between variables is that there are numeric and nominal variables. Numeric variables are also called quantitative variables. The terms are used interchangeably. These are typically what we think about when we think about a variable. So a numeric variable is a variable whose values are numbers. And usually the higher the number, the more of the thing or the attribute that there is. So in the previous example in which you were asked to rate your excitement about statistics on a scale from 1 through 10, the higher the number means more excitement, and the lower the number means less excitement. The other major type of variable is a nominal variable. The term nominal comes from the idea that its values are names. Nominal variables are also called categorical variables because their values are categories. So for example, one nominal variable is biological sex, and the values there are female or male. A person's score on the variable biological sex is one of those two values. Another example of a nominal variable might be psychiatric diagnosis. Possible values could be major depression, post-traumatic stress disorder, schizophrenia, obsessive compulsive disorder, etc. Some more examples would include ethnicity, nationality, personality type, marital status. Okay? These are all variables for which a person's score places them in a category. There are several kinds of numeric variables, so we can make further distinctions between types of numeric variables. In psychology, the most important distinction is between two types: equal interval variables and rank order variables. With an equal interval variable, the values of the variable stand for equal amounts of things being measured. So for example, temperature that is measured in either degrees Celsius or Fahrenheit is an equal interval variable, since the difference between a temperature of 18 and 20 means the same thing as the difference between a temperature of 31 and 33. In both cases, there's a 2-degree difference. Most psychologists also consider psychological rating scales as roughly equal interval. So the 1 through 10 excitement about statistics rating scale that I've been using as an example is considered an equal interval scale because it is assumed that the difference between an excitement rating of 4 and 5 means the same as the difference between a rating of 7 and 8. In both cases, it's a difference of 1, and that is assumed to be equal. Now there's a special case of an equal interval variable, which is called a ratio variable, or we could say that the variable is measured on a ratio scale. An equal interval variable is a ratio if it has an absolute 0 point. An absolute 0 point means that the value of 0 indicates a complete absence of the variable. So counts or accumulations of things use a ratio scale. For example, the number of siblings a person has is a ratio variable because a 0 means no siblings. You could be an only child, for example. We can also say that a person with 4 siblings has twice as many siblings as a person with 2. Other examples that are measured on a ratio scale would be physical variables like distance and weight and time. It's important to know that many variables, even most variables in psychology, are not measured on a ratio scale because there is not a true 0 point. The other main type of numeric variable is a rank order variable. This is a variable in which the numbers stand only for relative ranking. Rank order variables are also called ordinal variables. A student standing in his or her graduating class is an example. The amount of difference in the underlying GPA between the second and third in class standing might be very different than the amount of GPA difference between the 8th ranked student and the 9th ranked student. So a rank order variable provides less information than an equal interval variable. That is, the difference from one rank to the next doesn't tell you the exact difference in amount of what is being measured. Another example might be the place that you finish in a running race. The difference in time between the first finisher and the second finisher is unlikely to be the same as the difference in time between the second place finisher and the third place finisher, and so on. So the rank doesn't tell you the exact difference in the amount of what is actually being measured, as in GPA or time to finish the race. Another distinction that statisticians make is between discrete variables and continuous variables. A discrete variable is one that has specific values and cannot have values between specific values. So for example, the number of times that you went to a doctor in the last 12 months is a discrete variable. You could go 0 times, 1 time, 2 times, 3 or more, but you can't have gone to the doctor 1.72 times or 2.34 times. The number of visits is a discrete variable. There are specific times that you go, but there's no specific values in between the values of that variable. Nominal variables such as gender, religious affiliation, or college major can also be considered discrete variables. So in addition to being nominal, they are also discrete. Alternatively, with a continuous variable, there are in theory an infinite number of values in between any two values. So even though we usually answer the question, how old are you, with a specific age, like 19 or 20, you could also theoretically answer it by saying that you're 19 years old and 1 month. Or it would actually make sense to say that somebody is 19.26 years old, because there you can parse time into increasingly specific and small increments. So height, weight, and time are all examples of continuous variables where we can have an infinite number of specific values in between any two values of that variable. You can really just think of a continuum, an uninterrupted continuum. That's a continuous variable. It's important to note that many psychological variables are continuous, but rating scales typically only provide discrete options. Let's go back to this example. How excited are you about statistics? Please give a rating on a scale from 1 to 10. Most people are going to select a whole number, 1 through 10. Occasionally you might get people that say, well, I'm like a 7.5, right? But for the most part, the options that are presented are discrete. However, if you think about it, this attitude is really a continuous variable, because you could place yourself somewhere along the continuum from 1 to 10, and any value in between would actually make sense, right? It's possible to have a value of 6.33. So even though we measure things with kind of imprecise measurement where there's only discrete options, you need to think about conceptually, is this variable really discrete, or is there a continuum on this variable where an attitude could take on any possible values between 1 and 10? Thinking about different types of variables and level of measurement is important, because how variables are measured affects the statistical operations that can be performed. Data from nominal or categorical variables can't be used to calculate many statistics, such as an average, which is called a mean, which is something you'll learn about in a couple of weeks. This is because the numbers that we assign to categories don't have meaning. So we can do things like count the frequency of observations at a particular level of the variable. For instance, there's 60% women and 40% men in a particular college course. There are also statistics that we'll learn later in the course called the chi-square that are designed to find associations between categorical variables. For instance, we can answer the question, are men more likely to major in a certain subject than women are? Data from rank order variables also can't be used for many statistics. For example, educational level can be ordered, but we can't make assumptions beyond that. So we can't assume that the difference in education between being a college undergraduate and a high school student is the same as the difference between being a graduate student and an undergraduate student. And so for that purpose, even if we were to assign numbers, we couldn't calculate an average. Similar to categorical data, we can, though, calculate frequencies, percentages, and do chi-square tests. Interval and ratio data can be used for many statistics. This is because we can make arithmetic assumptions about the degree of difference between values. And so with this type of data, we can calculate statistics such as the average, standard deviation, correlation coefficient, and do all the statistical tests that you'll learn in this class. All right, we're going to move on and learn about displaying data. So I'd like to start with an example. And this is in the textbook. So in this example, students in an introductory statistics class during the first week of the course answer the question, how stressed have you been in the last 2.5 weeks on a scale from 0 to 10, with 0 being not at all stressed and 10 being as stressed as possible. Now in the actual study, there were scores from 151 students, but to make this an easy example, we're just going to use a representative subset of scores from just 30 of these 151 students. So you'll see the 30 student scores that appear on the screen here. Now looking through all these scores gives some sense of some overall tendencies. So for instance, we can see that the lowest score is 0, the highest score is 10. There seem to be more high scores than low scores, but what I gave you is not necessarily the most accurate summary of these data. So how can we do better? One way to do that is to summarize the data using a frequency table, and that's what was done here. In a frequency table, we have an ordered listing of the number of individuals having each of the different values for a particular variable. In this case, stress is the variable which has the values 0 through 10. Notice those are the possible values because those were the options that were given to students. What is your stress on a scale from 0 to 10? The frequency column in the middle represents the number of students that selected a particular stress rating. So for example, you can see that 4 students rated themselves as a 6, and 7 students rated themselves as a 7. Tables like this sometimes only give the raw number frequencies, or sometimes they'll give the percentages as well. In this example, we can see that in order to calculate the percent of students that have a particular frequency, we take the frequency at that value and we divide by the total number of participants. So we can say that 3.3% of the data, or of the students, had a stress rating of 0, because one student out of 30 is 3.3% of the data. What you should also see is that when you add up all the frequencies in the middle column, the sum of those frequencies will equal the total number of participants, which was 30. A frequency table is valuable because it makes the pattern of numbers easy to see. In this example, you can see that most of the students rated their stress around a 7 or an 8, and there was only a few students that said that they had a low stress rating. In this class, I'm not going to require that you make a frequency table, but I want you to understand the steps that are involved in making a frequency table so that when you see a frequency table, you understand how it was constructed and you can interpret it easier. So here are the steps. If we're doing this on paper, you would just make a list down the page of each possible value from the lowest to the highest, Go one by one through all of your scores, making a mark next to its value on the list. Then make a table showing how many times each value on the list is used, and then figure the percentage of scores for each value. And so that's what we would do, is essentially we just make a column that has all the possible values, and then we just start tallying how many of these scores had each of the values. It should be noted that the textbook suggests that you start with the lowest value at the top of the table, but it's also possible to order the values of the variable in ascending or descending order. So you can see descending order in the table on the right. Statisticians and researchers do it both ways. It's simply just a matter of preference. In addition, some frequency tables include for each value the total number of scores with that value and all values preceding it. These are called cumulative frequencies because they tell how many scores are accumulated up to that point on the table. If percentages are used, cumulative percentages can also be included. So cumulative percentages give for each value of the variable the percentage of scores up to and including that value. The cumulative percentage for any value or for that score having that value is also called a percentile. So you might have previously heard the term percentile or percentile rank. Well, that's also known as a cumulative percent. Cumulative frequencies and cumulative percentages allow you to see where a particular score falls in the overall group of scores. Okay. So here I have definitions of both cumulative frequencies as well as cumulative percentages. And just to give an example of how we interpret cumulative percent and how that relates to percentile, we could look at a stress rating of 9, and then we look over at the rightmost column and see that 9 is associated with a cumulative percent of 90%. What that means is that somebody with a rating of 9 scores in the 90th percentile because they have a score that is as high or higher than 90% of the other scores. So again, why do we use frequency tables? They describe the data, they make the pattern of data clear, and they show how many scores there were for each value on the variable or on the rating scale. Now sometimes there are so many possible values that an ordinary frequency table becomes awkward. In these cases, we used a grouped frequency table, which is a frequency table in which the number of individuals, the frequency, is given for each interval of values. An interval is a range of values that are grouped together. So I'll illustrate with an example, and this also comes from the textbook. So in this example, researchers had 94 psychology students keep a diary of their social interactions for a week. Each time a student had a social interaction lasting 10 minutes or longer, he or she would record it. So what we see here is the number of social interactions lasting 10 minutes or longer over the period of a week for these 94 students. So we've got these 94 data points. And looking at them, it's kind of difficult to make sense of what the pattern is. Well, one thing that we could do is we could follow the same process as we did with an ungrouped or ordinary frequency table. Is we could just identify all the possible values and then go through our list and just basically tally up how many times that value appears in our data set. What that would yield is an ordinary or ungrouped frequency table. What we can see is that it's a lot of information and not really the best summary. It's not much of a summary at all. So it's better to group the values. This is what a grouped frequency table looked like. What you can see is that the value of the variable, which is the number of social interactions in a week, have been grouped to create an interval. We see the interval in the leftmost column. Now there are some guidelines for creating intervals and for creating these grouped frequency tables. So the first guideline is that a table should use anywhere from 5 to 15 intervals. In this example, there's 10 intervals, so that falls within the range. The number of intervals that appear in the table will be based on what the width of each interval is. So the width of each interval should be a simple number, like 2 or 5 or 10. What you can see here is that the interval width is 5. The next guideline is that the bottom score of each interval should be a multiple of the width. And so if we just look at each of our intervals, and we go from 0 to 5 to 10 to 15, etc., we can see that the bottom of each interval is a multiple of the width of the interval. And finally, all of the intervals should be the same width. So when you're looking at a grouped frequency table, you'll know that it's done well or it's done correctly if that table follows all of these guidelines. All right, so the next thing that I want to talk about is how to use graphs to display data. So using graphs is another good way to make a large group of scores easy to understand. And so a straightforward approach is to make a graph of the frequency table. And so a kind of graph using information from a frequency table is called a histogram. So in a histogram, the height of each bar is the frequency of each value in the frequency table. And then, let me just get my animations, there we go. And then ordinarily in a histogram, all bars are put next to each other with no space, giving the appearance of a city skyline. So this is what it looks like. So on the y-axis, what we do is we make a scale for the frequencies that goes from the lowest value to the highest value. Oh, and I should note that what we have here is we're just making an ordinary a histogram from an ordinary frequency table that came from our example of the stress ratings of the 30 students. So the process is to really start with that frequency table, to put the values along the horizontal axis from left to right, starting with the lowest value and moving to the highest. On the y-axis or vertical axis, make a scale for the frequencies that go from the lowest value to the highest value, and then make a bar above each value with a height for the frequency of that value. Again, you won't necessarily be constructing any histograms in this class, rather just viewing and interpreting them, but I think it helps to understand how they're made in order to understand how to interpret them when you see one. It's also possible to construct a histogram based on a grouped frequency table. Here you see a histogram that was constructed from the social interaction data from the 94 students. You'll notice that what is labeled on the horizontal axis is the midpoint of the intervals. Specifically, we see the midpoint between the bottom of each successive interval. So 2.5 is the midpoint between 0 and 5. 7.5 is the midpoint between 5 and 10. When you have a nominal variable or categorical variable, the histogram is called a bar graph. Since the values of a nominal variable are not in any particular order, you leave a space between the bars, and it doesn't necessarily matter what order you put the categories in. Frequency tables and histograms describe something called a frequency distribution, which is the pattern of frequencies over the various values of a variable. A frequency table or histogram describes a frequency distribution because each of these shows the pattern or the shape of how the frequencies are spread out or distributed. Psychologists will also describe the shapes of frequency distributions in words. And so there's three main terms or characteristics that can be used to describe frequency distributions, which are modality, skewness, and kurtosis. So I'll speak about each of these three. So first, starting with modality. Modality refers to the number of modes or peaks in the distribution. So really the question that we answer is whether the distribution's shape has one main high point, or we could think of this as kind of a high tower in the histogram. So for example, in the stress rating data, if you go back and look at it, the most frequent value, in other words, the mode, is 7, okay, the value of 7. This gives the graph only one very high area. This is known as a unimodal distribution, where there's one value that clearly has a larger frequency than any other. If a distribution has two fairly equal high points, it's called a bimodal distribution. And any distribution that has two or more high points separated by a lower frequency is called a multimodal distribution. Strictly speaking, a distribution is bimodal or multimodal only if the peaks are exactly equal. However, psychologists use these terms more informally to describe the general shape. Okay, and then finally, a distribution with values of all about the same frequency is called a rectangular distribution. Oh, I also wanted to add, it should be noted that a bimodal distribution is a special case of a multimodal distribution with only two frequencies. So, right, okay. Just wanted to show you some examples of histograms I created using a statistics software, just to give you some sense of what real world data looks like. Here's a unimodal distribution, one clear mode. Here's a bimodal distribution. Again, the two modes are not exactly the same, but we can say it's more or less bimodal because we have those two clear peaks. And then here's a multimodal distribution. All right, so the next characteristic to describe distributions is skewness. And so what we're talking about is whether distributions have symmetry or a lack of symmetry. A symmetrical distribution is one in which the pattern of frequencies on the left and the right side are mirror images of each other. A skewed distribution, on the other hand, is one in which the scores pile up on one side and spread out on the other side. So it's a distribution that is not symmetrical. In a skewed distribution, there's one side that is, you'll see that it's kind of long and spread out, and we call that the tail of the distribution. The side with fewer scores, that is the side that looks like the tail, is considered the direction of the skew. So skewed distributions can be either positively skewed or negatively skewed. I'll describe each one a little bit more. So a distribution is positively skewed when there's many scores that pile up on the low end and the others spread out across the high end. We say that it is positively skewed because the tail, or the skew, points in the positive direction. So it's really the direction that the tail points that gives the skew its name. So we've got positive skew because the tail is on the positive end or pointing in the positive direction. So when we have many scores that pile up on the low end, it may be because it's impossible to have a score that's any lower. This is called a floor effect. Here's an example of where that might happen. Here's some data that I previously collected. I asked students to rate the extent to which they disagreed or agreed with the statement, "Statistics is not useful to the typical professional." The lowest rating was 1 disagree, and we see the scores start to pile up at a value of 1. So there's a floor here because it is impossible to give a score that is less than disagree the way that this question is asked. So we have a floor effect. It's impossible to have a lower score than disagree. There can be other examples of how to get a positively skewed distribution. So for example, the number of children in a family could produce a positive skew. It's impossible to have a number that is less than 0. So you could have 2 parents that have 0 children, in which case the bottom of the scale, the floor, there's a floor to that scale and it's impossible to go below. So scores in a particular sample, scores might pile up, especially if you have a sample that includes many people that are not parents with 0 children. Similarly, it might be more rare to have very large families in which there are many children. That would yield a positive skew. Another example of a positively skewed distribution might be the results from a really, really difficult test. If the test was very, very difficult, you could have many people that don't get any questions right, in which case, or that answer very few questions right, in which case the scores tend to pile up at the bottom and there's only a few high scores. All right, now on the other hand, we've got a negatively skewed distribution in which most of the scores pile up at the positive end and then spread out across the low end. Again, it's a negative distribution because the tail of the distribution is pointing in the negative direction on the number line. A negatively skewed distribution can be caused by an upper limit or by a ceiling effect. So in this particular example, the question was, I can learn statistics with a rating scale of either 1 to 7, ranging from disagree to agree. And we have most people indicating that they agree that they can learn statistics, and so scores are kind of piling up there, with very few people disagreeing that they can learn statistics. Okay, so the rating scale only goes up to 7, so we have a ceiling effect there. Another good example, though, of how we might get a negatively skewed distribution is to think about a very easy multiplication test that's given to adults. So most adults know their multiplication, and so you would expect that if it's given to a sample of adults, most adults are going to score very high, and many are going to get a perfect score of 100%. Well, you can't do better than 100%, so most of the scores are going to pile up at that very upper end, and there would only be a few adults that would get a bad score on a multiplication test. So those are just a couple examples of how we might get either a positive skew or a negative skew in some real-world examples. All right, so the third way to describe a distribution is in terms of its kurtosis. And so with kurtosis, we're describing a distribution in terms of whether the middle of the distribution is particularly peaked or flat. The standard of comparison is a bell-shaped curve. In psychology research and nature more generally, distributions often are similar to this bell-shaped standard, which is called the normal curve. We'll discuss the normal curve in quite a bit of detail in later chapters and in later lectures. But for right now, the important thing is that the normal curve is unimodal and symmetrical, that has a peak at the average. And so that's what you see on the left side, a normal curve. Kurtosis then refers to how much the shape of a distribution differs from a normal curve in terms of whether its curve is in the middle is more peaked or flat. Departures from the normal curve can be described as either leptokurtic or platykurtic. Leptokurtic distributions are very peaked and usually have more scores in the tail of the distribution than the normal curve. It's as if the normal curve got pinched in the middle and some of the scores went up into the sharp peak and the rest spread out into thicker tails. Distributions with a flatter curve usually have fewer scores in the tails and are flatter in the center. And so that's what's known as a platykurtic distribution. In this figure, we can compare the general forms of kurtosis. When there's positive kurtosis, the curve is too peaked in the middle and with too many scores in the tails compared to normal. And when there is negative kurtosis, the curve is too flat in the middle with too few scores in the tails. All right, and I'm just going to close out, as the chapter does, talking about some controversies and limitations of using graphs, specifically the failure to use equal interval sizes and exaggerating proportions. So in this first example, this is also given in the textbook. This is a chart that was actually published in the New York Times some time ago. It shows commissions paid to travel agents by major airlines. The chart gives the impression, if we look at those white bars, that commissions paid to travel agents dropped dramatically in 1978. However, a close reading of the graph shows that the third white bar for each airline is only the first half of 1978. Thus, only half of a year is being compared to each of the two preceding years, which were full years. Assuming that the second half of 1978 was like the first half, what this information would actually tell us is that in 1978, there'd actually be an increase rather than a decrease. So for example, Delta Airlines estimated full year 1978 figure of 72 million, which is much higher than in 1977. So the main point is, when presenting information in a bar graph, the intervals that are presented need to be the same. Okay, moving on to the next issue would be exaggeration of proportions. So here's one example. The height of a histogram usually begins at 0 or the lowest value of the scale and then continues to the highest value. On the left, we see a histogram that does not follow this rule. It shows the average housing price in a particular region over a 4-year period from 2008 to 2011. By starting the vertical axis at 150,000 instead of 0, the graph appears to exaggerate the changes in housing price over time. Now, the graph on the right shows the same results, but in this case, the vertical axis starts at 0. What you can see is that the change in the average price does not look nearly so dramatic. So it's pretty interesting to note the differences between the two graphs. On the left side, it looks like a big drop in price. On the right side, not at all. So it's a good lesson that graphs can be manipulated to try to make a particular point. All right, and then another guideline is that the overall proportion of a histogram or a bar graph should be that the graph is about as wide as it is tall. So the proportion should be 1 to 1 or 1 to 1.5. Right, and so that's what we see in the upper left-hand corner, that correct proportion. Look what happens if we make the graph look much shorter or taller. Okay, so we see the two examples, one on the bottom where the graph is too short and wide. We see another on the right where the graph is too narrow and tall. So this effect is kind of like using a computer software to alter a photograph of a person. The true picture is distorted, and what we get is that the particular shape of the histogram gets distorted. And so what you can see when the histogram is too wide, it makes it look like there's much more of a skew. When it's too tall and too narrow, it looks like there's no skew at all. So we want to try to have our proportions be about as wide as it is tall, and this has been adopted to give people a standard for comparison. Changing that proportion misleads